In this last video of Chapter 9, we're going to be looking at a practice problem looking at the modeling of the spread of a disease. So the setup here is we have, during World War I, a particularly lethal form of flu killed about 40 million people around the world. We're going to focus on where this epidemic started, which is in an army camp of 45,000 soldiers outside of Boston. The first soldier fell sick on September 7th, 1918. And with time t in the days since September 7th, we have this SIR model that's susceptible, infected, recovered, where we have the differential equations that we introduced in the last video. The same differential equations. Again, what changes from disease to disease and situation to situation is the constants of A and B. Here our constants are 0.000267 and 9.865. This gives us some idea of the infectiousness of the disease, A, and then how long it takes people to recover. So we're going to answer a few questions about this example problem. So here we go. First one, what are S naught and I naught? That is the initial values of susceptible and infected people. Well, at the very beginning, we are given that there is one infected person. So I naught is going to be 1. That is the first soldier fell sick on September 7th. That means that the number of susceptible people is not 45,000, but 45,000 minus the one person, which is 44,999. Because we have 45,000 soldiers total, we're not given any information that anybody's immune in any kind of way. So everybody's susceptible, but again, that just means that one less person because that one person is infected. So next question. Same setup, we're just going to repeat the setup here, same thing. What is the threshold value? And we're given that this threshold value has the equation B over A, just involving those constants. So this is going to be 9.865 divided by 0.00267. And that is going to give us a value of about 36,948. So the next question past that is, how do we know that this model is going to predict an epidemic? How do we know that this is going to spread across the population that we have, or that it's just going to die out slowly, or maybe quickly, it's just going to die out? We know that because the number of susceptible people, S naught, which is 44,999, is greater than that threshold value, 36,948. So because of that, we know this is going to be an epidemic because S naught is bigger than the threshold value. If it were less than that, we wouldn't expect the disease to spread like an epidemic, given this model. So last question here, which is kind of a big one, is that we are going to look at the differential equation di ds, and we're going to solve the differential equation to approximate the number of soldiers infected over the course of the disease. So the first question here is to find di ds. We did this in 9.6, but the way we're going to do this is just look at di dt over ds dt. And you can think about the dt's are going to cancel out. What's really going on here is an application of the chain rule. And if you want to go back and look at the definition of the chain rule, you can see some similarities in what we're kind of doing there. But we can just think about the dt's cancel out. We have di over ds. This is how we're going to build it. So this differential equation is going to be ASI minus BI over negative ASI. And we can simplify this. We can break up the numerator. So we can write this as ASI over negative ASI minus bi over negative asi, and a bunch of stuff cancels out. We have everything in the first fraction is going to cancel out, and then we have an I in the second that's going to cancel out, plus the negatives. And this will give us a negative 1. When ASI cancels out, we're left with a 1. Negative 1 plus B over A. We can write this as S to the negative 1. Or B over SA, or B over A times 1 over S. All those are the same thing. So here's our differential equation. di ds equals negative 1 plus b over a s to the negative 1. And we can think about solving this because this is going to be kind of like, so this is like solving dy dx equals negative 1 plus b over a x to the negative 1. And since it just involves that x value, or in this case the s value, we can just find this by doing the integral. So we can say that I, the number of infected people, which is what we want to see here, is going to be the integral of negative 1 plus b over a, which is a constant, s to the negative 1 ds. Think about it as x if you want to. And this will give us a value of negative s plus b over a, and the antiderivative of s to the negative 1 is natural log of s plus our constant of integration. So now we are going to solve, or find, I should say, find our value of c. And we're given the initial condition that I naught equals 1, S naught equals 44,999. So here we can say when 1 is equal to I, we have negative 44,999 plus B over A, which we know is about 36,000 or 37,000, natural log of 44,999 plus C. Moving everything over to the other side, we have the 44,999 is going to give us 45,000. We add that over, minus the B over A, natural log of 44,999 is going to be our value of C. So our differential equation is going, or sorry, our solution is going to be negative S plus B over A natural log of S plus this value of C. I'm going to write that on the next page, and we're going to do a little bit more with that problem. So our solution here is I is equal to negative S plus B over A natural log of S plus C, and C was 45,000 minus B over A natural log of 44,999. All right, so we found our solution, and now we have one more question, which is how many people were infected total? So what we're going to do is we know that the disease has run its course. It's over when the number of infected people is 0. That means that the disease cannot spread anymore. It is now over at that time. So we are going to try to find when I is equal to 0 in this equation. So we're going to solve this equation. Now, we're not actually going to do this algebraically. In fact, it's very difficult to do algebraically. We could do this graphically. meaning that we could graph this function I over S, and I think we get something like this kind of graph. And we can say when I is 0, we have that S is about 30,000. All right, if this were an equation that we could do algebraically, we could just figure that out. But let's just say we could just draw that graph on some online graphing calculator and get that the S-intercept here is about 30,000. So that means that total, so at the end of the disease, S is equal to 30,000. I is equal to 0, which means that the number of recovered people is equal to 45,000 minus 30,000, or 15,000. And that's the number of people who have contracted the disease and now recovered. So going back through this, just real quick, this is just one example of what we could do with these differential equations. We could answer questions about some initial conditions, and this is going to be an epidemic or not. We could analyze these values of A and B. And this last question was a lot we could do with it. We can, in this case, find the solution, the number of infected people per susceptible people. We can answer a question about like how many people are going to be infected total. This is not very easy algebraically. You shouldn't try to do it. I don't think it's really even possible with any methods that we have able to do that. But you could do that graphically and estimate about 30,000 people at the end of the disease. And again, what that means is there's 45,000 people total. We know that at the end, I is 0. There's 30,000 people left in the population who are susceptible, which means they haven't gotten the disease, they're susceptible, and they're not going to get the disease. Everybody else, 15,000, are the number of people who have gotten it. You're going to look at some other example problems with these differential equations, probably none as difficult as this one, but again, there's just different things you can do. And all of this is just looking at a couple big application problems of differential equations and what they mean and how we can deal with it, how an integral can give us the solution in some cases, how to find the value of C, and so on and so forth.